Unit 3. So Unit 3 starts off with calculations with the mole. So to do calculations with the mole, we'll have to look at Avogadro's hypothesis. Avogadro's hypothesis states that equal volumes of different gases at the same temperature and pressure will contain the same number of particles. So using moles, let's try an example. So let's try to find the molar mass of iron and chlorine. So there are 4 atoms present here and 3 chlorine atoms. So the steps here would be to 1, find how many of each element are present, and 2, write it out. There's no number right here like there's here, so there's no number here, which means there is only 1 iron. So you would do 1 times 55.8. So now you may wonder, what is 55.8? It's the atomic mass. So where you can find the atomic mass is right under here, 55.8, and there is 1 iron. So we're going to times 55.8 by 1. And then you can see there are 3 chlorine, and chlorine's atomic mass is 35.5. So then we're going to add 3 times 35.5 because there are 3 chlorines, which is 162.3 grams. So again, we got the molar mass by doing 1 times 55.8 plus 3 times 35.5. And we also have conversion factors. So we know that all elements have a specific mass in grams for 1 mole itself. We can use this conversion factor for any element in finding their mass or number of moles. All we have to remember is X amount of grams is equal to 1 mole, or 1 mole is equal to X amount of grams. Next, we'll talk about standard temperature and pressure. This term right here can be shortened for STP. And STP at 0 Celsius, 1 mole of gas that occupies exactly 22.4 liters. And 22.4 liters is something that you'll have to remember because it'll come in handy later. And this number right here can only be used for gas. So now let's try an STP example. So let's try to calculate the number of moles of 0.120 liters of NO2 gas at STP. So let's start off by writing number of moles equals 0.120 liters, as you can see right up here, times 1 mole over 22.4 liters. Remember when I said to remember this number for equations? This is exactly how you'll be using it. So now what you're going to do is 0.120 times 1 equals 0.120, and then you divide 22.4 liters. And liters cross out, so they cancel each other out, and you're left with moles. It equals 0.00535714. But you see, this number does not work well with sig figs. So sig figs in this equation, you should have 3, has 1, 2, 3, 4, 5, 6. So what you're going to do is you're going to put it in scientific notation. And this is the answer in scientific notation. So what I did was I moved the decimal point back 3 spots, hence 10 to the power of -3 and 5.36. So if we go back to moles, let's talk about what a mole is. A mole is the amount of particles in something. Particles can be things like atoms, ions, molecules. The number of particles in something is a very large number, so we use Avogadro's number. However, this number is very large as well. So what we do to this number is we put it in scientific notation, just like we did with our last example, with 6.02 times 10 to the power of 23. So this number right here is put into scientific notation, and we'll be using this number forward as Avogadro's number. It'll be 6.02 times 10 to the power of 23 particles per 1 mole. So next is multiple calculations. From going to one another of these, is there any similarity that you see? The one similarity in how we go from one to the other is moles. each one has moles. So that is single step. And when looking at multi-step, you go from your starting unit and you go to moles to find what you're looking for. Get percent composition. So it's a pretty easy topic, so let's explain using an example. Superphosphate, molar mass of this compound right here. The molar mass, we have 3 times 63.5 plus 2 times 31.0 plus 8 times 16.0, and we have a total molar mass of 380.5, and I can explain how. So percent of copper. So what I did was I took the number of atoms of copper and multiplied it by its atomic mass and divided it by its total molar mass of the compound. Then you times it by 100% to get the amount of percent element is in your compound. And at the end, it should equal 100%, all your elements. Next, we have the empirical formula. This is known as the simplest formula. So let's learn this in an example as well. I have 64.86% of carbon, 13.51% of hydrogen, and 21.62% of oxygen. We're going to use a chart like this right here. So we make sure to assume the sample is 100 grams. So if the sample is 100 grams, we have 64.86 grams, 13.51 grams, and 21.62 grams. And as you can see here, you take the grams and multiply it by a mole over the atomic mass to get how many moles you have in each element. And then you take the lowest number of moles you have and you divide it by each element to get numbers to make your empirical formula. Once we took our moles, and right here you can see oxygen has the least amount of moles, so I divided each element amount of moles by oxygen's amount of moles to get 4 carbon, 10 hydrogen, and 1 oxygen, and that gave me C4H10O. Next we have our molecular formula, which is equal to molar mass over empirical mass. Our example C4H4O will turn into C8HAO2. I took the molar mass of C4H4O on top and put the empirical mass at the bottom and divided the two and got 2. So this number right here, we'll use it to multiply our example, which will make it C8H8O2. Next is molar concentration. Things to remember: density equals grams per milliliter, area equals meter square, and molarity equals mole per liter. Another name for molarity is also called concentration. C equals molar concentration, so the unit would be M. N equals number of moles. V equals volume in liters. Some terms to know: concentrated and diluted. When you are writing concentrated compounds, you put square brackets around them. Last but not least, we have dilution. Always work with high concentration things. Basically means acids that are very concentrated are very dangerous to work with, so we dilute them less concentrated. So to do equations for dilution, we use this right here. C1V1 equals C2V2. C1 is concentration before dilution, V1 is volume before dilution, and then on the other side of equal, C2 is concentration after dilution and V2 is volume after dilution. Last example today will be about dilution. So if 20 milliliters of 400 m sodium chloride is added to 80 milliliters of 0.900 m sodium chloride, what is the resulting concentration of sodium chloride? So since we are looking for the resulting concentration of sodium chloride, we'll be using C2. So C2 is equal to C1 over V2. And we'll be having to use 2 solutions. So for solution 1, we have 20 milliliters times 400 m over 100 milliliters, which equals 0.08 m. And for solution 2, we have 80.0 milliliters times 0.900 m over 100 milliliters, which equals 0.720 m. We're still paying attention to sig figs in both the solutions. We're going to find the total concentration of sodium chloride by adding the two molarities together, which is 0.800 molarity, and still notice how we are keeping an eye open for sig figs. And that's it for Unit 3. Thank you for watching.